now go on to our next problem here. Definition of absolute extrema. And we've been talking about relative extrema. Did we talk about absolute versus relative on last Thursday? If I want the absolute, I'm talking absolute maximum of a function, which variable am I talking about? Again, Stephanie, the output. I want the absolute maximum output value of the derivative, or excuse me, of the function, or the absolute minimum output value. So keep in mind when we're talking about this, we're talking always about output. Let's put this in the notes here. We're talking about output values. Okay. Let the function be defined at some input C. Okay. This is so similar to what we had before. It's almost ridiculous. Do you recognize this terminology here? The function is a relative maximum of f of c is a relative maximum if there exists an interval containing c such that, but the only difference is it's for all x. Now again, it's almost identical to that I'm going to just kind of wave my hand at this and just say I want the absolute utmost maximum or minimum value of the output I can find. And that's all we're going to say. Let's look at an example. By the way, let me go back to my to this one here. Is there, remember the function's the one that the cubic one, is there an absolute maximum output value for this cubic function? No. Because it's going to continue going up, 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 and down, down, down. Okay. Now, if, and this is where the if comes in, if I said between, let's say -1, so we would stop it right here, between -1 and, let's say 4. Okay? Between -1 and 4, is there an absolute extrema on this function? What would you say? Yes, because it is in fact in the interval, and nothing else exists except between inputs of -1 to inputs of 4. Then I would have an absolute maximum. So you can have an absolute maximum in a closed interval, even an open interval, that may not be true if you open it up to infinity to -infinity. Okay? So we just have to kind of keep your eye on a lot of the problems. I don't know if you've hit these yet, but I know the Calc 1 homework has hit them, where they're given something like this, and they're given a closed interval, and they're asked for an absolute maximum. A lot of students will make mistakes because they don't consider the endpoint. Okay, the endpoint could be where the absolute extrema occurs, even though the whole function may not have an absolute on it. Okay, well, again, those are so close in nature. Let's see, we did something like this, I believe, in class, didn't we? It might have been, maybe it was the Calc 1 class. So let's do this one. And again, I don't know if it's 46 or not, so we'll scratch that out. Graph a function on the interval from -2 to 5. Question, inputs or outputs? These are inputs, okay? So for inputs between -2 and 5, having the given characteristic, the relative minimum is at x equaling -1. The critical number is at x equals 0, but it's not an extrema. Okay? Absolute max is at 2, and absolute minimum is at 5. Okay, I'm going to stop here. I like the way that Philip has interpreted the critical number but no extrema here. Okay, notice that he came down and used that. At this point, if we were to draw a tangent line, it would have 0. Now, the only thing I don't know about is a relative minimum at -1. Okay, I think you kind of missed that, didn't you? Relative minimum at -1. So somehow we'd have to maybe turn this. In fact, if you were to, yeah, and this is a, did you see that as 1 or -1?
I did it on the sheet with it, but I saw it as negative.
Because it looks like you see it as 1.
Yeah.
Okay, well, you know, just for him, just for Philip, we'll just make that a positive. Okay? Then it's correct. Okay. If you had it over here, you'd have to kind of almost do a reverse, a mirror image of that. But assuming that it's a positive 1, he's got a relative minimum here. This is 2, almost got it there, a maximum. And then a minimum here. And so if this is 5, we just got to stop it there. Okay, an absolute here. And he made sure that that was higher than what he started over here at -2. Okay. So again, I like that because it makes you think a little bit. Yeah.
So the reason 0 is a critical number is we ended up showing because it just had a slope of 0.
Yes.
Like it doesn't matter what the output is.
Yes, because it isn't a critical number where the derivative is 0.
Yeah.
Yep. That's exactly it. Now, to do another one would be a little harder to do. You know, what I had here was, it's almost like that cubic curve, where if you have a cubic, where it almost is not even a function at that point. It's so steep. I made mine's too over exaggerated. But the cubic curve, or cube root curve, I should say, looks like this. And as you get in here, you've got a derivative that would be almost vertical. And that's what I was trying to do here. It's not a very good picture. I like his better. Okay, so we'll do that. Let's go on. One of my favorites. Okay, here we go. Let's just kind of tear it apart here. Trachea, contraction. What's a trachea? Yeah, it's in your throat. Okay. Anyone having any trachea contractions lately? Well, if you're coughing, you do. Okay? So I guarantee that we're all going to have some trachea contractions sometime in the next 9 months, whatever, when we get the colds or the flus. Forces the trachea to contract, okay, which affects the velocity, and velocity v, that's what we're going for here, of air passing through the trachea. So as you cough, it's a little more forceful because it's constricted. Air is going through like a straw. Okay, suppose that the air during coughing is this. Now, who came up with that? I don't know. Someone who made some observations and decided that this would model the velocity going through our trachea when we're coughing. Now, small r, we got to figure out what that is, and capital R. K is a constant. I don't know what the constant is. I don't know what it's dependent on. Probably on maybe age or you know, how tall we are or whatever. R is the normal radius of the trachea. Okay, K is a constant. What about capital R? Is it a constant? Or is it a variable? Again?
It's a variable.
Okay, so your trachea right now has a certain radius. Are you saying that your normal trachea is changing? The radius is changing? Normal? No, not during coughing. Normal. Non-coughing times. Is your trachea changing? No. So is capital R a constant or a variable? It's a constant, okay, because it's the normal, it's the non-coughing one. And small case r is the radius during coughing. That's the one that's a variable. So of this formula, how many variables do we have? Well, we only have 2, don't we? Input is radius during coughing, and output is velocity. Okay. Your radius during coughing, does it make sense that it's 0 less than or equal to r less than capital R?
Yeah.
When you're coughing and it's contracting, I don't think it's going to get larger than what it is normally, right? So it can't go greater than capital R. Can it go less than 0? Let's hope not, okay? Let's hope not. Okay, what radius will produce the maximum air velocity? That's the question. Now, I've got to go change a light, a shade back there. Velocity, which means we want to maximize the value of V. V is a what, an input or an output? Output. If you want to maximize an output, let's just go back to our other problems here. If you want to maximize an output, what are we looking for? The derivative, and where the derivative changes sign, and where the derivative, if the derivative is 0, okay, that's a good place of a possible extrema. So if we're going to maximize this output variable, we're going to look for or determine what derivative. Derivative of what? Okay, the output with respect to what? It's the only other variable, right? Don't confuse capital R with small case r. They're two different things here. Okay. Now it looks as if I've got 1, 2, 3 factors I have to consider. Really? Do you believe that? Or could I simplify my function first so that I don't have 3 factors, 1, 2, 3? Do what? Yeah, okay. So tell me how, Garrett?
Maybe just take the distributed property of K and R minus R.
So what do I come up with?
K times big R, normal radius, minus K little r times R squared.
Okay. And then use the product rule? Or could I do more? I mean, you can do whatever you want, okay? I'm just giving you some options here. So if I want to find that derivative, what is K capital R? Constant. Okay, like a coefficient. You might as well have said 2. Okay, same thing. So what's the derivative? I'm going to write it out here. Derivative with respect to R of K capital R, R squared, minus the derivative with respect to R of K R cubed. Now you might say, but I'm going to have to use implicit differentiation. Well, not really, because it tells us that those are constants. And again, it's just like putting up a 2 in front of the R squared and a 5 in front of the R cubed. We don't have to go quite that far. So we take the derivative, the coefficient times what? 2, the exponent, and then subtract 1 from the exponent. Okay, so treat these as coefficients. Minus, take the, yeah,
3K R squared.
R squared, exactly. So let's see, I've got 2K cap R, R, minus 3K R squared. That's my derivative. Okay, so first of all, I determine the derivative. Now I want to maximize velocity. So what do I do with the derivative? Again, Ryan? Set it equal to 0. Okay, so we set the derivative of velocity with respect to the trachea during coughing. It's a 0. And let's see. I'll just write it down, then we'll decide what to do. Anyone have an idea? Okay, so factor out, whoops, not the 2, but we'll factor out the k and small r. Okay, so I have 2 capital R minus 3k small r. Not the k, good. That's not okay. Okay, how about that? Sorry. So now we've got 2 factors set equal to 0. What do you know about 2 factors set equal to 0? 1 has to be 0. Or, so, what am I trying to find? Okay, I want to find what radius, what constricted radius is going to produce the maximum air velocity. So I have that when the radius is 0, think about it, think about it. Is it possible? What happens to you when your trachea constricts to 0 radius? You kind of can't breathe, right? Is that a good thing? No. Okay, you're not. Now remember, we're going for maximum. We're not saying which one's maximum, which one's minimum, right? If your trachea has constricted down to nothing, it's completely closed, is that going to be your maximum air velocity? Or is that going to be your minimum? Minimum, okay? So, that's not going to work. Over here we have that 2 cap r equals 3 small r. R is 2/3 cap r. So what's going to give you maximum air velocity? What's capital R stand for? Yeah. So if you can constrict your, now I want you, next time you cough, I want you to do this on purpose. Constrict your trachea to 2/3 of its normal size, and you're going to have maximum air velocity. Okay. Well, there's no way I can graph that for you because I don't know what normal is. What is it? I don't know. Figure out. Half an inch? No, it can't be half an inch. That's not an inch across. Maybe it is. Okay. Anyway. That's what we're talking about. That's the whole gist of that problem. Now, everything we're talking about is we now know how to take derivatives. Chapter 2 is all about how do you take derivatives. We talked a little bit about the applications and so forth, but we really were just in the process of taking derivatives. Chapter 3, we're beginning now, and we're going to spend the rest of the course talking about, so what? Where can we use this? How can it be used? Here's an example. We are given a situation where we have a formula for it. We have a function that allows us to given an input, to figure an output, and we want now to maximize the value of that output variable. It's going to occur where the derivative is 0. Take the derivative, set it equal to 0, you've got it. There's a whole section coming up on optimization, and that whole section is going to be doing nothing more than problems like this. So hang on, those of you who are tired of just doing endless practice problems, we're going to have those where we can actually apply them. I'm going to stop this and go on now to section 3.3.